Thanks, everyone. I'm going to start this presentation off with a little poll. So please raise your hands if you've ever played with ChatGPT or any LLM. Yep, at this point, I expect most of this room to have their hands up. Keep your hands up, actually. So keep your hands up if you use ChatGPT or any LLM for that matter, about like once a week. Cool, still see most of the hands here. How about twice a week-ish? Every other day? Cool, less hands, but still like about half the room. How about every day or like most days you use ChatGPT LLMs? Wow, that's a good amount of the room. Yeah, you can go ahead and put your hands down now. I just wanted to get a quick pulse of how familiar we are with LLMs and also just show how cool, how prevalent it kind of is now. Like if we think about this in the context, 2 years ago, this LLM term wasn't even widely known. 1 year ago, ChatGPT was just released a couple months ago, and we're just starting to see how cool it was. And now we're starting to get to this point where we're trying to deeply integrate LLMs into our workflows. And yeah, as a machine learning engineer, pretty excited about that. So today I'm going to talk about one way we can integrate LLMs into our security workflows. And we're going to explore this idea of fine-tuning LLMs for security log detections. So just a quick introduction of who I am before I start. I'm Wilson Tang. I go by he, him pronouns. I'm a proud second-generation Asian American. And also quick shout out, it actually happens to be my mom's birthday today, and she's watching from home, so happy birthday, Mom. Yeah. Thanks, everyone. Yeah. Cool. So in my current role, I'm a machine learning engineer in our threat hunting team at Adobe. I attained my master's degree in computer science from the University of Washington in 2022. And some of my hobbies include cooking, love to cook, traveling, love to eat new food in new places, and video gaming. Love to play this game called Valorant. All right, quick agenda of what I'm going to go over today. I'm going to talk about traditional security log detections and kind of some of its limitations. And the way I'm going to go about it is go into this case study of command obfuscation detection. And then we're going to go into a brief LLM overview and then talk about how we're going to fine-tune LLMs specifically for command obfuscation detection. And then I'm going to make some generalizations for other use cases we can start to think about. So let's dive right into it. Let's talk about traditional security log detections. And when we think about this, we're usually thinking in this rule-based realm where we're looking at our log events and we're looking for certain signatures, predefined signatures in the events. For example, like, is this process executing some known malware? Is this login coming from some blacklisted ASN? All these sort of things. But what if our detection needs something more sophisticated? What if it needs something a little more quote-unquote dynamic? I know that's a pretty loaded term, could be used very gimmicky, but here I'm just trying to talk about ways that we're trying to write detections that can't be easily written in a simple query. And here at Adobe and our threat hunting team, we're trying to use machine learning to address some of these concerns and combat this. And now with this big LLM boom, we're seeing a lot of use cases mainly for text generation. So we're looking at mostly like personal assistants, stuff like that. But in this project, we're going to look at how we can leverage LLMs, or can we leverage LLMs for classification tasks? And specifically, can we leverage LLMs for classifying our security log detections correctly? And now I'm going to start talking our specific case study in command obfuscation detection. All right, so before we can actually start detecting it, let's just go over what it is so we understand what it is. So command obfuscation is a technique to make a standard command line intentionally difficult to read, but still execute the same functionality. So in this example here, this comes from a talk from a couple years ago that was really good on obfuscation. So you have this sample command line up here, and then in the obfuscated part, you can see there's a bunch of special characters, but both of them will still execute the same functionality. And the main danger here really is that we can have a lot of these mature detections on our command lines, but a lot of them could be rendered basically useless if an attacker is able to obfuscate their commands maybe slightly, maybe a lot, and it would evade some of these certain detections. And just a side note, not all obfuscation is malicious. There are definitely operational use cases of this. For example, maybe using like base 64 encoding to shorten these command lines, but just so we know the nature of it there. And also in this presentation, we're just going to talk about detecting obfuscation. We're not going to be concerned with de-obfuscating any commands, but that is also another pretty cool use case we can start thinking about leveraging LLMs for too. All right, now I'm going to dive into some other techniques other than fine-tuning LLMs for detecting this command obfuscation. Some of it will contain some machine learning, so at this point, I'm going to go over it sort of quickly, so don't be too, don't worry about understanding it completely all the way through. I'm just trying to get a big picture of what other techniques exist so we can understand why we are leveraging fine-tuning here as well. So the first way, not machine learning, but maybe more in the static rule security log detection space, we can think about just doing some rule-based logic here. So for example, we can ask the question, does this command line contain a specific percentage of special characters, maybe like 50, 70, 80%, something like that. And hopefully by that question alone, you're kind of seeing that it's not super flexible. We'll need a lot of manual tuning, maybe more rules, maybe more sophisticated rules to get well, just to get it right. But at the end, we might not be able to curate a good set of questions and to actually detect obfuscation because it is a pretty big, broad realm, and it won't necessarily generalize well for all sets of obfuscation. So now let's jump into some machine learning techniques. We're going to start with a simple one called logistic regression. And in a very crude summary, you can boil it down to like a learned equation that outputs a probability between 0 and 1. And that's sort of illustrated here in this diagram on the right, where this is the logistic regression line. And you have your group of data that's closer to 1, and you have a group of data that's closer to 0. And you can imagine that like maybe the obfuscated one data is like towards the 1 and the non-obfuscated is towards the 0. And basically with this process of logistic regression, we're just trying to learn this equation that would get us to this scenario. And how we're going to get there is that we're going to go through this process of feature engineering. And what we're going to do is we're going to choose certain features in the data that we think are important for classification. So for example, maybe character frequency matters. So like the frequency of the letter A, B, C, all the way down to Z. Maybe we care about the frequency of special characters like semicolon, commas, periods. Maybe we care about the strength length. Maybe we care about entropy, like the randomness of a string. Maybe we care about white space density. You can go on lists and experiment with all, and this is the process of feature engineering. And then when you have your nicely curated set of features, you're going to pass it into the logistic regression equation. It's going to try its best to learn the weights to match the data, and hopefully at the end you'll get some sort of representation that looks like this nice diagram on the right. But in in more simple cases, you're going to get to here, but in more complicated cases, you're not going to necessarily get to this spot. It really relies on just having a really nice set of curated features, but also something important to note for this specific point is that logistic regression will start to fail when you pass too many features into it. So that's why we're trying to think about more solutions here. So now let's step a little closer into the LLM realm, and we're going to talk about more traditional, quote unquote, traditional deep learning, even though it's a sort of still kind of new field. What we're going to do in this deep learning approach is that we're going to use this thing called neural networks, and then what it'll let us use is that we're not going to need to do any of this like feature engineering in deep learning. We're really only going to need to pass in a vectorized representation of the data, and what I mean by that, it's much more simpler than the feature engineering. So in the sample here, we're going to give it the whoami bash command and then convert it into some characters. So you can imagine that each number corresponds to each character in the command line. So W is the 24th letter in the alphabet, H is the 15th, O is the 20th, and then so on. And you have this numerical vectorized representation of data. And then what you're going to do with this vectorized data is that you're going to pass it through this thing called a neural network, which I'm also going to say it in a really crude summary. It's boiled down, it's a giant matrix multiplication operation, and then at the end you're going to get an output that's either obfuscated or not. And what we get out of here is that we get more generalization than the logistic regression technique, and we don't need to do any feature engineering. But the hard part of deep learning is going to be experimenting with different model architectures and trying to find the right model architecture that'll actually fit our data well. And that's where we're going to jump into LLMs. So two main things have really enable LLMs to go far. And the first thing is this thing called the transformer architecture. And if you don't know what that is, it's highlighted in this paper called Attention is All You Need from 2017. And this is an amazing paper to read. I'm not going to go into the details of this in this presentation, but it's a great paper to understand the basis of how LLMs work. And yeah, it's still how it's being done today, like just stacking more transformer layers on top of each other. So it's a really good way to understand the context. And the second thing that really enabled LLMs to go far is because of this transformer architecture primarily, is that we're able to train on terabytes of data and many days, weeks of GPU time. So on the right, this is an older data set of Llama 1 from Meta. This is one of the popular ones that actually open source release their data sets of what they train on and the exact proportions and the disk size and everything. And you see Llama 1 train on terabytes. At this point, the newer models probably train on hundreds of terabytes, maybe even petabytes at this point. Who knows at this point? But yeah, there's a lot of data that goes into this. So where I'm trying to get to with why we're trying to go for this fine-tuning approach is because there's really no need to quote-unquote reinvent the wheel. And what I mean by that is that it's pretty costly, pretty time-consuming to pre-train these models from scratch. So what we can do to simplify this process is we can take the model checkpoints from the internet, and then we can do this fine-tuning process by continuing to train the model on our own custom data set. And this data set, when we fine-tune, can be relatively small because the model's already pre-trained, it already understands language. We just need to pass in some smaller data to actually tweak the parameters in the model to make it work on our data set. So next, I'm going to go through a sample template code review, walkthrough. So I don't really want you to be too nitty-gritty about understanding the complexities of every code bit. I just want you to understand the overarching concepts behind the code so you understand what this whole process of fine-tuning entails. So the first thing we want to do is we got to get our data set first. So in this context of command obfuscation, maybe we can do something like grab some command line events from our environment, run some open source or manual obfuscation tools to create some synthetic data, or maybe grab some obfuscated commands if we got them. And then we can create some template prompts with these commands to create our training samples. So in this example up here, this is a simpler illustration of what your prompt can be. We can go into the specifics of maybe prompt engineering here, but not going to touch on that here. But here for this prompt, we split out into some sections. So like the first one is the description of the problem. So below is an instruction that describes a binary classification task for command obfuscation detection. Then we'll follow it up with an instruction prompt. So analyze the following bash command line. If the command is obfuscated, output yes, or if the command is not obfuscated, output no. And the input will pass in the command line, and then the output will be yes or no. You can imagine if the input was obfuscated, we would want the output to say yes instead, so we can train on this. And here, now that you see this training sample, you can see this is a sort of hacky approach to simulate binary classification. This isn't like the traditional way that we might think of binary classification, like we see in like the logistic regression example, where we're just trying to output a probability between 0 and 1. Here, this is a more hacky approach just to say, hey, we want the output to be yes or no from the LLM. And now let's actually go into the code to do some of this importing importing the LLM. So the LLM specifically we're going to use in this presentation is Llama 2 7B. At this point, it's already outdated at this point. There's Llama 3 out here, and every week it seems like there's a new LLM being released boasting the best benchmarks. We're also looking into Microsoft Phi 3 right now because pretty small LLM, pretty good. And also, this is going to come from Hugging Face, which is, if you don't know what Hugging Face is, it's a popular open source or popular repo, kind of like GitHub, specifically for machine learning models and data sets. All right, so before we actually import it, let's set up some quantization to reduce our GPU memory usage. And why this is necessary is that these models, even like 7B, is going to take a lot of GPU memory. And why it does is because regularly these LLMs are going to be storing 4 bytes per parameter, which means the precision of the model, like each parameter, each weight, or each number, if you'll go with me on this, each number in the model is going to be 4 bytes in precision. So if you have 7 billion parameters times 4 bytes per parameter, that's going to take 28 gigabytes GPU memory just to import the model. That's not even including any of the data that we need to put into the GPU as well. And that's a lot of GPU memory. Like we're not going to be able to use a lot of like commodity GPUs. We're going to need the more expensive ones like the A100s, H100s. So if we want to be able to leverage some cheaper GPUs, we got to set up some quantization. So what that means is that we're going to reduce the precision from about 4 bytes to 4 bits instead, which is substantially less. So you got 7 billion parameters times 4 bits parameter, and we'll get like 3.5 gigabytes of GPU memory. And that's much less memory that we have. And this is just some config to set that there. And next, we're going to import the tokenizer from Llama 2. And what the tokenizer is going to do for us is that it's going to do this vectorization of the data for us, so we don't need to manually do it ourselves. Imagine back at that deep learning side, we were doing the who I am and convert it into that vector ourselves. This tokenizer will be, importing tokenizers will be able to do this for us. And it's not just more convenient for us, but it is quite necessary to do this because Llama 2 was trained on its own tokenized representations of the data. So we can't just pass in our own tokenized examples and expect it to work because it just won't. So we are going to have to use Llama 2's tokenizer for the model to work here. And this is just some code to import it. Important thing is probably just the model repo name at the top. Other parameters not going to talk about. And then finally, we're going to import this model from Hugging Face. So same model repo name, and then pass in the quantization config to get the model in and quantized. And now one best practice before we actually start running the fine tuning is actually to test the model outputs before doing any fine tuning. Because if the LLM actually just works out of the box on our task, then there's really no need to fine tune it ourselves. So what we're going to do here is that we're going to run our raw text through the tokenizer. And the raw text, you can imagine, is that template prompt from a couple slides back, except that we're going to remove the output section. So no yes or no, just output and then blank, because that's what we want the model to generate for us. And then there's a line in there that's like max new tokens equals 1. That means we just want the model to output 1 new token in the output. So we just want the model to output yes or no in our example. And all these other nice parameters that we can do. And finally, we can print out the outputs, do some stats on it, and get some bare metrics before we start. And then finally, load in the data set, get a train data set, get a test data set, train data set we actually train on, test data set we actually run some eval on. And now let's talk about how we're actually going to run the fine tuning. And the first way we're going to do it is this method called parameter efficient fine tuning, PEFT. And this means we're only going to fine tune with a small number of model parameters. So instead of fine tuning on on all the 7 billion parameters, we're only concerned with fine tuning a small number of parameters because that's going to make our process faster, and that's all we really need. PEFT is a popular Hugging Face repo that contains multiple methods for fine-tuning, and the more popular implementation of this is called LoRA, which is low-rank adaptation, and this is a technique to reduce the number of parameters being fine-tuned with matrix low-rank operations, and that's all I'll say about it. It'll get very mathematical, try to explain it, but for the purpose of this talk, we're just going to say that, and this is a popular way to do it, and this is just a way to define, and in the code, this is some common configs that you set for LoRA. And then finally, we're going to prepare our training arguments, so pass in some per device train batch size, gradient accumulation, learning rates, max steps. That's super important, but you'll get some training arguments. And then finally, we'll pass it, put it all together and pass it into our trainer. So pass in our model, pass in our training data set, pass in our PEF config, our tokenizer, and training args. And finally, we'll run trainer.train. And trainer.train, depending on how big your GPU is, how big your data set is, how fast your GPU is, it could take a matter of minutes to fine tune, it could take a matter of hours to fine tune, but at the end, you'll get your final fine tune model. And then finally, you can run your model outputs after that, run some metrics on it like we did before, and see how your model improved after that. And hopefully, after going through this amount of code, we can start talking about some of the advantages of fine-tuning compared to the other methods. So first advantage is that we really abstract most of these traditional machine learning processes away just by starting with a pre-trained model. So what I mean by this is that we don't really need to do the feature engineering because we're kind of in this deep learning realm. There's no model architecture experimentation because we're using the straight model from Llama, so we don't need to play with the architecture. We're just using its model architecture. There's no more manual vectorization. We're just going to use the model's pre-trained tokenizer instead. And all we're really concerned about here is providing the model with our raw data set instead. And one other note to emphasize here is that with fine-tuning LLMs, we're more concerned about the data quality. So passing in good quality data to actually fine-tune our model on, because that is the most important part here. And not to say that that doesn't exist in other ML problems, it actually does. There's a saying that in ML, data quality, data preparation is the most important step in machine learning, so you should always concentrate on that. But with the fine-tuning, you can abstract a lot of the other processes away and just focus on the data set itself. So I just went and tried to convince you on how fine-tuning is a great approach, but this really wouldn't be a fair or a complete presentation if I didn't give you some of the trade-offs of using fine-tuning LLMs. And the first trade-off I'm going to say is that, do we really need all these 7 billion parameters for this classification? And I'm going to go ahead and say, probably not. These 7 billion parameters are really good for generating text, and necessary for generating text. But when we're talking about classifying data where we just need a yes or no, we might not necessarily need all these 7 billion parameters to get the correct classification out of it. And typically, this is going to require more GPU memory time. Even though it's substantially less than trying to pre-train an LLM from scratch, we're still going to need that. Still going to need a GPU and some GPU cycles to actually fine-tune the model. But even with these trade-offs, these are kind of the trade-offs we make for quote-unquote ease of use, abstract these ML processes away, just storing our data set at the LLM and fine-tuning. It's easier to use. We just need to throw a little more compute at it, which, I mean, money is also tough too at this point with so many GPUs out there. But what I really want you to get out of this is that even though it's not the most perfect approach, every approach is going to have its trade-offs. Fine-tuning is just this new tool that we can consider when we're developing security log detections. So as a good machine learning engineer, maybe as a good security practitioner, we should be leveraging, considering all our tools and all different approaches we can use for developing these detections. So, and then we can make a good, clear final decision at the end after we evaluate it all. So just some closing thoughts here. Applying this for other use cases, you can generally just replicate most of these steps, just kind of copy paste for your own various use cases and replace the data set with your own. To be very honest out here, this code very similarly you can find in many open source repos, many blog posts online. This fine-tuning approach through the Hugging Face library is pretty standardized out there, and a lot of people are doing similar things. But if you want to get more see this presentation in particular, and you want to stay in touch with this, I'm going to be posting updates on this, so you can add me on LinkedIn. You can stay tuned. I'll be doing more updates, and I'll at least post this B-Sides talk if you're curious about this code as well. So yeah, I hope you at least learned one new thing out of this presentation and deepen your perspectives on LLMs here. Thanks for listening, and I'll go to the Slido now.
Well, that was amazing. Thank you so much, Mr. Tang. We do have one question. As a machine learning engineer, how do you think AI will affect the security industry and future jobs?
That is a loaded question. I'll talk about it in the context of the security log detections. I think that I think it'll really help propel us to do new types of detections. So not just LLMs, but talking about stuff like anomaly detection and also all the other machine learning approaches that I think it'll just enable our security analysts to have more tools to do more mature types of detection. So I think there might just grow the security industry more and just make us more mature.
Fantastic answer. Well, thank you so much, Mr. Tang. We really appreciate you coming out and presenting. We actually have something special just for you. And for our audience, if you have further questions for him, please feel free to meet him up in the City View area. And our gifts are actually coming from Socket Security this year, one of our main sponsors, and we are so grateful for that. Obviously, we couldn't do this without our volunteers and our sponsors, so we much appreciate it. And we really appreciate you coming out, sir. Thank you so much. Fabulous job. Fabulous, yeah. So we